Thank you, Steve. A business card. I'll keep it. So we're doing well on time. Next presentation is from Andy Lee. There, found him. So Andy is an engineering colleague who will be telling you about spectrum mapping. Right, Andy? I just want to say, right after Andy's presentation, we'll take a 15 minutes break. You'll have coffee and some drinks outside the room. Thank you. Andy, you have the floor.
Hello? Okay. Thank you. So I'm here to talk about TV whitespace databases. What exactly is a whitespace database and what do they do? But before I jump into the details of the database, I do want to kind of take a little bit of time to go over kind of the key motivations. Why would we build a whitespace database and why we think that's important? So right off the bat, it almost goes without saying that spectrum is in high demand. After all, it's a finite resource. We can't just create new spectrum whenever we want it. When we talk about trying to increase available spectrum, what we're really talking about is finding better ways to use, reuse, and share the spectrum that we already have. So even though you can't technically add spectrum to the pool, what you can do is increase this notion of the virtual capacity or potential for spectrum to deliver something of value. And that's where we think whitespace databases can add a lot. So if we look at TV deployments as it is used today, we all know from personal experience that TV is not fully occupied. As you're flipping through channels, you'll notice that there may be half a dozen, maybe a dozen or so TV channels that are used, but actually the vast majority of TV channels are empty. It's been this way for decades. And here, if we look at a map of the US, you can get a more visual feel for what that looks like and why that is. So this map here is showing just one channel. So it could be any channel, but let's say this is channel 20. And if I were to say, what are all the TV broadcasts that are on channel 20? This is what it would look like, where green is showing where there is a signal present, and all the dark areas are empty, not used. If I were to flip to another channel, you could see that, okay, the deployments are a little different, right? The transmitters are slightly different locations, maybe with different power levels. I can continue to do this, looking one channel at a time. And you see that they kind of dance around. If you look at any one location, there is no consistency or pattern to the channels that are occupied. So no matter where you are, you kind of get a random mix of TV channels that are occupied and ones that are empty. So one thing you'll notice is that there is a lot of empty space in between transmitters. This gives you kind of a visual feel for what are the areas that there might actually be room to share. So these are not fully occupied, they're not densely populated, and the other thing that you will notice is that the transmitters are spread out this way by design. The TV technology has all these broadcasters that want to fit in the same amount of spectrum, and they got to figure out how to best utilize that. And of course, they're going to spread themselves out as much as possible, both in space and as well as in frequency. And this minimizes the amount of interference that they would cause on each other. So some people may also have the idea that, well, why don't we just relocate some broadcasters and open up some spectrum that way? And that's fine, and it could technically be done, but there is, you have to keep in mind that broadcast infrastructure is something that is a heavy investment, right? It takes months to years, maybe some decades, for the broadcast infrastructure to be built out. And this represents a real investment in broadcast equipment, tower construction, filters, antennas, power amplifiers. There's quite a lot of infrastructure that goes into this. And to say that I'm simply going to relocate things is not that easy of a thing to do. So there's significant cost and time associated with trying to do that. And then if you look at the US model, they've estimated that it could be in the hundreds of millions of dollars to even $1 billion if you wanted to actually relocate TV broadcasts to get them out of the way, to clear spectrum that way. And when you look at those numbers, you have to understand, how are you going to find the money? Who's going to pay for this? And how are you going to get the whole thing to be executed in a timely fashion? No trivial thing to do. The nice thing about going with a white space database solution is that you don't have those kinds of problems because you don't have to move anybody. The TV broadcasts can continue to stay exactly how they are, operate exactly as they have always done, both on the broadcast side and the receivers. Broadcasters don't have to change anything. The people watching TV don't notice any difference either. So the now you have to keep in mind that you're now able to unlock all those blue areas that you saw on the previous map to create new spectrum without taking away anything. So you haven't disrupted any of the broadcast operations, but you also haven't taken away spectrum from someplace else to make it available here. Now, another interesting feature about white space databases is that you can consolidate all that complexity, trying to take the data, run the availability calculations, put all that responsibility into the database, and you can actually keep the white space devices fairly simple. You now get the power of very dynamic radios, systems that can adjust as they change location or as TV broadcasters come and go. The radio spectrum may change, but the devices automatically adapt. And they don't need to have all the complexity of having to compute what is the available spectrum inside the device. This keeps the devices very inexpensive, and it gives them that very dynamic capability without adding much cost. So now let me get into what actually makes up a white space database. So the first thing you need is data about the transmitters that you're trying to protect. So this means a few basic things like their location, how much power they're putting out, what channel they're on, their antenna pattern. Once you have that, you can compute what is their emission, what kind of RF energy are they launching into the environment, and that kind of defines what is the spectrum that they are occupying, what is used. Then we add some terrain. So in this example here on the map, you have some transmitters that we had around our Cape Town trial area. You can see you now have information about the transmitters themselves, plus you know a little bit about the environment surrounding them. And so these transmitters in the Cape Town environment against the natural terrain, you can see they're going to be impacted by some mountains and things that may be in the way. So the next thing you want to do is run some propagation modeling calculations. This will kind of give you the broader picture and the details of what spectrum is actually occupied. Where is this radio energy going, and what areas do you want to protect and stay off of? So here's an example of what it might look like to see the occupied spectrum for one transmitter. There's a transmitter in the middle here, and kind of the green area is where there's going to be strong signal. Blue is going to be a little bit less, and the violet areas are going to be very weak signals. All the rest of the space is basically empty. You can see how the terrain will block the signal in some directions and less so in others. So you do this for all the transmitters. Now you have this very comprehensive picture of where are all the places that spectrum is occupied. The next thing you want to do is find what is available or what is potentially safe to use for white space devices. And so you run some interference avoidance calculations to find what is the available spectrum. You can think of this as kind of the inverse or the complementary spectrum to what is occupied. So here's a picture if we map out what is that available spectrum. This is for the San Francisco area. And a very common question I get is, well, how much white space is available in San Francisco or some other city? And I can't give them a simple, straight answer because it's fairly complicated. If you look at this map, you can see kind of how the coverage area for the many broadcasts in an area, and this is one of the more rich broadcast environments where you have potentially hundreds of TV broadcasts, each on different channels with different powers, serving different markets, different antenna patterns, and they overlap and crisscross in pretty elaborate ways. And then when you do the inverse of that, finding the complementary spectrum, what's available for white space, it's equally complex. And you can see that here, that the amount of white space that you really have depends very much on the exact location that you're talking about. You move a little bit in one direction or another, the amount of spectrum could change. But the great thing is, the white space databases, once you've set up this system, will do all these calculations for us. So we can find, pinpoint for any location what is available. So now imagine that you take this channel availability map, if you will, and overlay that with a population density map. So kind of the intersection of where the people are and where the channels are available can tell you how many people will be served by how much spectrum. And so you do that exercise, and this is the result you get. So if we look at the blue bars, this is kind of the distribution of if every person in the US was to ask the database, what spectrum is available at my location? This is the distribution of the kinds of answers they would get back. So if I look at a particular example, like the column for 60 megahertz, so that's like maybe the 10th column in, for about 13 million people, they would get an answer back saying you have 60 megahertz available. The blue line running across this graph is showing the cumulative population coverage. So if, as an example, if I look at the 75% population level, this is the number of people that would get this X amount of spectrum or more. So at 75%, you would see that there's roughly about 42 megahertz or more would be delivered to 75% or more of the population. At the 50% level, you're looking at something more like 72 megahertz. So a large portion of the population is getting quite a bit of white space spectrum. And this is even in the US, where there's a fairly robust deployment of TV broadcasts. So we've also done the similar exercise with transmitter data from Senegal. So here's a map showing the occupancy of the TV spectrum throughout all of Senegal. Just indicating the number of TV channels that are occupied. So you just mentally do the inverse of that or find the complementary spectrum of that, and you'll find, okay, this is the amount of white space that is there. Since there's not that much occupancy of the TV spectrum, that means there is a lot of white space available. So this is almost a very boring map. It's entirely green. There are 11 or more white space channels available pretty much anywhere. And again, if you do that exercise of overlaying a population density over the availability map, we get a similar chart as before, but very different result. So here you can see that there are pretty much for 100% of the population, no matter where you go in Senegal, you will find that there's at least 100 megahertz of underutilized spectrum available. Some will have more, but as a minimum, there's 100 megahertz of underutilized spectrum available. So lastly, one other important task of the white space database is to provide access for the devices to actually query. Right? They need to actually be able to ping the database saying, here's my location and what is available at my location. So that's the last final key part of delivering the services of a white space database. So let me shift gears a little bit. The other thing I get really excited about is kind of the power of data. So now you have all this information that's come in, and you've gathered propagation modeling algorithms, terrain data, and all this transmitter data, and you've blended them together, and you have this toolbox of really powerful things to let you examine and analyze the data that's there. And I'm always a firm believer in if you have good data, it leads to better decision making. Right? You don't want to be making decisions in a void. So having information available is very, very beneficial. So you can do simple things like get high-level overviews of the transmitter landscape. So here, again, is Senegal showing the locations of all the TV transmitters with an overlay that's actually showing the relative signal power. It's kind of the RF energy that's being put out into the environment. Very simple, it's quick and easy to do, but this is much, much easier, in my opinion, than looking at page after page of numbers, right? Coordinates and power levels. It doesn't make that much sense. You put it on a map, very easy to understand, very easy to dig into. You could look at individual records. here's another example of a transmitter. We get to see what is the serviceable area. Where is the power going? What areas are not served? Are there any places where the RF energy is bleeding out, if you will, into areas where you don't necessarily want it? But you can look at those kinds of details because all the tools are at your disposal. There have been cases where we get data and we put it on a map and we notice some errors in the data. Today we have the power of a lot of web maps, overhead, aerial photography, satellite imagery, Google Earth type tools. And when you have all your transmitters in this electronic form and you can go look at them, you'll notice a few quirks sometimes. In this particular example, we had a TV transmitter with coordinates at the red triangle. But when you zoomed into the aerial photography and looked, there's nothing there. There's some bushes. But you notice, 100 meters away, that this looks like a tower here. There's a building. I can see the shadow of a tower and cables running. So you can see that, okay, there maybe been a data entry error, and we can easily fix this. And in some cases, this actually makes a difference. So when you're looking at the propagation characteristics of a signal, if you're next to a mountain where actually most TV transmitters are actually installed, this can affect drastically how much the shadow or the direction of the signal will travel. So it's good to correct these things. Another exercise we went through was comparing and contrasting the differences of a transmitter's configuration. Here we were comparing an omnidirectional TV configuration with a directional one. So on the left, you have the omnidirectional case where I can understand where sometimes as a TV broadcaster, you're using a directional antenna, but you don't actually have that information at your fingertips. It's not entered into the database. So you have to kind of make certain assumptions. And an omni antenna would be a conservative assumption, so you can make sure you're protecting them and maybe even overprotecting them. But you can see the difference between these two images is that the one on the right, where you've now actually plugged in the correct directional antenna information, has a lot less kind of leakage signal or blowback signal off the back side of the antenna. The intended target is just to the west, into the kind of the mountainside right there. And you can see that this could drastically affect how much white space is available because you don't have all that signal kind of wandering off into areas that you don't actually intend to serve. So this kind of emphasizes that accuracy of data is very important. The better the data, of course, better data in equals better data out. And if you have the right information, you can optimize how much white space you can make available. And one final example is where we looked at the contention between two transmitters that happen to be on the same channel. So if you imagine looking at the overlay for one broadcast and then a different one at a different location on a different channel, and where they kind of overlap or intersect, we can kind of highlight those areas. A lot of times there may be interference going on, and if you don't actually see it, you can't tell immediately where that's going to happen. So mathematically, we have all the tools now. We can emphasize that or put focus there. So we know that if there is this signal contention, we can say that, well, if there's going to be any interference, it's most likely to be seen at these locations first, because these are the most vulnerable places. This may be high on a hilltop, or they may be in a particular location that has to be facing both transmitters. And this lets us explore those places and actually ends up saving quite a bit of time and effort. Because if you need to go out there and take measurements, why am I seeing interference, or where is it coming from, or what was the potential, you can just go directly to these places instead of wandering around randomly and hoping that you'll find out where the problem is. So there's actually a lot of other things that we do to try to analyze and understand data. We can do lots of what-if comparisons. If we have the data and then we want to shift the parameters for some rule up or down by a few dB, or change some distance calculations by a few kilometers one way or the other, you can tell, what is the impact? How many people are affected? How much spectrum becomes available, doesn't become available? Where are the places that are affected? We've also seen some interesting kind of byproducts that weren't anticipated. So after the FCC announced their white space rules and we implemented this, we saw kind of peculiar interactions between neighboring markets. So in the upper right corner here, we have a picture of what it looks like around Chicago and Milwaukee area in the US. So in Chicago itself, or in Milwaukee, the city to the north, white space availability is fine. But what nobody anticipated was kind of the the overlap between them is actually the place where you have the minimum amount of white space. And it works out that way because of the way they define the rules. And until you actually see this on a map, you wouldn't actually know that this was going to happen. And so it's interesting to now be able to visualize it, see it, and see, is there anything else that we want to adjust or compensate for? And again, because you have all this data in a great electronic form, you can quickly examine local RF environments. Pick a point. Now you know how many channels are on the air, which ones, which direction they are, what's the signal power. Lots of stuff becomes now easy to do. So I'm going to end my presentation with the statement that I think that white space databases really opens up tremendous possibilities, just lots and lots of possibilities. And it all begins with a very simple step of having the data available. So I'm really encouraged to see so many people here, and want to emphasize the fact that if you make the data, publish the data, it becomes so easy to plug it into the rest of there's so much work that industry has done to build up white space databases and all the tools associated with them. And you can immediately get on the path to doing better spectrum sharing. So, by all means, consider, what is available, how you publish the data, share it, and, we can do a lot with it. So, I think that's.
Thank you, Andy. I have a first question. I'm taking the first question. I think it's great. You have done a great presentation, and I have a question about. I think many people here in this room are, especially regulators, are wondering what are the impact of TV white spaces on digital dividend? What are the implications on it? Could you clarify that?
Yes. So in the charts, the graphs that I was showing earlier about population versus amount of spectrum available, this was all mirrored off of FCC rules where they've already done their digital dividend, and so we're only considering frequencies below 700 megahertz. So it's kind of already factored in that none of that 700 megahertz and up would be counted here. So it wouldn't change the picture that I've shown here. It's sort of already forward-looking to consider that.
It means that in Senegal, below 700, we have 100 megahertz available for TV white space.
Exactly.
Is that correct?
That is correct. That is
amazing.
Absolutely correct.
All right.
Okay, thank you, Andy. I'm Chumora from Malawi, University of Malawi. The presentation is really exciting, and what I see is where you've converted the national band plans into a digital thing, electronic representation of a given national band plan. And I still see that it's static because you have to read in, put the data, and then if there is any error, you may adjust, which I think still is electronic, but it's still static. I'm asking if there is a possibility to be able to all these base stations, for example, make them, give them an IP so that they, as you hinted a little bit of that, so that they can get the data of their situation, the channels they're operating at, the polarization whatsoever, a script of that, and feed into your system, a database. The database integrates all this, including the power, the transmit power, because that would be obviously adaptive. And then eventually be dynamically, updating the data itself. Is this possible? And yeah, thank you.
Yeah, thanks for the question. It is definitely possible to take feedback from the device. I think you're talking about having the devices report back. I've got what spectrum you said was available, and I plan on using X, Y, and Z. At the moment, this is really just trying to kind of a read-only mode. So Ofcom has actually given this some serious thought, and they've actually written into their requirements that the devices must report that back to the database. But they're still hesitant to actually act upon that data because there's potential consequences to doing that. You don't want people to somehow artificially reserve spectrum by pre-allocating stuff that they're not really going to use. I could say, oh, I'm using all this spectrum in all these different locations, and if that somehow diminishes the answer that other people may get, you don't want that to be happening. But it doesn't mean it can't someday happen if we figure out, what are the right rules and kind of decision points that you would make along the way. The first step is get the database to collect this data and examine it. Again, the power of data will let you make better decisions about that down the road.
I have 3 questions here. Yes, go ahead first.
Thank you very much for the beautiful presentation. My questions are...
Could you present yourself, please?
Okay, my name is Engineer Austin Nwaulune. I am the head of Spectrum Administration for Nigerian Communications Commission. Question 1. Are there the same opportunities for TV white space, for digital, and for analog? Like in Nigeria, where we are currently still on analog, and we are going digital, are there the same opportunities for us? Number 2, now that we are going analog, we are going digital, how does the adoption of TV white space, how is it affected by this timing? Or rather, how does this affect our timing?
Okay, so the first question
There's the third one.
That's still the first one, okay. So.
The third one is, how many, like in Senegal, where they have 100 megahertz available for TV white space, how many operating companies can be accommodated there if it is unlicensed? Like in Nigeria, for instance, you find operating companies not wanting to go do Wi-Fi in the 2.4 and 5.8 because according to them it's congested. Are we going to have the same scenario with TV white space? Thank you.
Okay, so I believe the first question was, what is the impact of the transition from analog to digital? There shouldn't be any. So the intent of the whitespace database is to constantly synchronize with what is known about the RF environment. So we would always be getting the latest information about where are the analog transmitters as well as where are the digital transmitters. And all of that factors into the calculation of spectrum availability. So as transmitters come online and older ones may go offline, the data automatically updates. As far as the whitespace devices are concerned, they don't even need to know. So they just give their location, they get an answer, and that answer may change. So even in the case of Senegal, where you have maybe 100 megahertz a day, the exact channels that are available might be different from one city to the next. But the device doesn't really need to know. It's just that when you add up all the pieces together, you're getting at least 100 megahertz. So I believe that also covers the second question about, if it affects the transition to digital. It should not. So the TV broadcast industry can do the transition on their own schedule, and it should not matter. The database will automatically adapt. And then the third question about congestion, I think you will find just adding spectrum to the pool is what you're really after here, right? The reason you have congestion is because there is not enough. And so you need to do whatever you can to make more available. And this is adding to the pool. You can't, we're not at this stage talking about a high-level kind of spectrum management or utility management. It is maybe something to consider down the road. The database does provide you with the tools to explore that possibility, right? Today, you don't have that option. We don't know where the 2, 4, and 5 gigahertz deployments are, how many there are, how much spectrum are they actually using, what's the percentage of utilization that's actually happening on that spectrum? We have no idea. But now that you have a database, and if you can collect information about what is actually being used, how much, and where, you can now look at it, explore it. And we're not quite there yet, so I don't have an answer as to how you would try to balance or make better utilization of the available spectrum. But at least the tools and the data is there, and we can start having that conversation, and we'll see where it goes.
Great. If just 1 minute, if I reverse his question to ask, what's the impact of transition on TV white space availability?
So that will depend on how many transmitters are actually occupying spectrum, right? So the database is there to protect. And if there is an overlap period, which does happen in a lot of countries and during the transition period, you may have like almost a dual network active, both analog and digital transmitters that are simultaneously on the air. During that time, sure, there may be some slight reduction in the availability of white space, but eventually you expect that, okay, the analog transmitters are going to go offline, and then the digital ones will remain. And then you return back to this abundance of spectrum, perhaps even more so if the digital broadcasts are more efficient about how they use that spectrum, and you don't actually need quite as many TV channels to serve the same amount of viewership.
Guys, we're going to take only 2 questions because we are quite out of time. But Andy is here, and he will be available for questions and everything and demos during the break session. You will meet him in front of this room. So we'll take only 2 questions and go to break. For the other questions, you can ask to Andy directly. You can grab him. There. No, here.
Russell Southwood from Balancing Act. I want to take the thought that the Malawi colleague was posing of the databases in real time. Presumably also you can get to the point where you record the time used on particular spectra by people, operators' devices. So eventually you'll be able to say that MTN uses X% of the spectrum for X% of time, or amount of time. And you could then say, well, actually, they're underutilizing their spectrum, so something could be done about that. And if you push the logic all the way through, you could say, well, we could charge them by the minute. So you have a completely different charging model. And I just put that out there because I think the logic is there if you think about it.
Absolutely. There's a lot of ideas circulating about what are other smart things you can do, both from a technology perspective as well as from a business perspective. Having billing rights or some kind of light licensing, if you will, to have a reservation for some period of time is one possibility. There's lots of other ideas, perhaps like micro auctions or other types of dynamic spectrum allocation and actually paying for it. But we're still so early in the process. It's definitely a little bit premature to try to project what may eventually become. But I love the fact that these are ideas and conversations that people are having because it really is opening up so many possibilities for better spectrum management.